Okay, this is a lecture on storage elements, both capacitors and inductors, the basics of these storage elements, which should have pretty much been covered in your physics class. So first of all, capacitance has units of farads, and what capacitance is the ability of an element to store electrical energy in form of an electric field. Uh, your fabrication of a capacitor is just two conducting surfaces separated by an insulator, and the amount of capacitance depends on the area of the plates, separation of the plates, and also the material of your insulator, which is called a dielectric. And from your physics, there's this relationship between the charge that builds up on the plates of the capacitor and the voltage across the plates of the capacitor. It's a direct relationship, as you can see here, and C is the capacitance. So where capacitance has the units of farads, you can see that a farad is equal to a coulomb, the unit of charge, divided by a volt, which is the unit of voltage. Okay, so a farad is equal to a coulomb per volt. Well, in circuits, as we've mentioned, what's really important is the relationship between the current and voltage for a particular element, because this is what defines the element. So the circuit equation for a capacitor that relates its current to its voltage is obtained by taking our expression here from physics for Q and plugging it into our equation for current. That current is just the rate of change of charge. So if I just take CV here and plug it into the derivative, I come up with that the capacitor current is equal to its capacitance times the rate of change of voltage across its plates. Okay, so this is really, from a circuit's perspective, an important equation for capacitors. And one very important characteristic of a capacitor is that the voltage across the plates of a capacitor cannot change abruptly. There's a couple of different ways to reason this. One is the understanding that the voltage across the plates of a capacitor is the result of the charge that builds up on the plates, and it takes time for this charge to build up. Okay, it takes time for that charge to collect. You know, as it builds up and collects, the voltage increases, and as the charge diminishes on the plates, the voltage also diminishes because of this direct relationship. But you see, because it's a buildup of charge or a lessening of charge, it takes time. So that's one explanation. Another explanation is just mathematically that if you have an abrupt change in time, then dt here is going to be very small. You know, if you were to consider that abrupt change to be instantaneous, where dt would equal 0, well, then you would have an infinite current, which means an infinite power. So another way to look at this is that in order to have an abrupt change in voltage across a capacitor, it would require a substantial current and therefore a substantial power. Now we're going to look at the case first here of an initially uncharged capacitor in a circuit that is charged up over time. So if we go to my notebook here, here's a circuit where we have, as you can see, a source Vs. Here's our capacitor symbol, and notice that the capacitor starts off with 0 volts across its plates, meaning that it has 0 initial stored energy. So energy has units of joules, so initially there's 0 joules stored by this capacitor. Now this switch, this symbol here represents a switch that closes at t equal to 0. Okay, t equal to 0 being the moment in time where we have a change in the position of this switch. So before t equal to 0, this switch is open, so you won't have any current flowing here. But then at t equal to 0, the switch closes, and now current's going to flow since this source is connected up to the side of the circuit that has the capacitor along with this resistor. So to come up with an expression for the voltage across the capacitor as time progresses past t equal to 0, we just use some circuit analysis. So as you can see here at node A, we did a KCL equation, just IR equal to IC. We write this current through the resistor in terms of voltage using Ohm's law. So the voltage across the resistor is just the voltage on the higher end side here where the current enters, which is Vs, minus Va, which is equal to the voltage across the capacitor, since we only have the capacitor connected between node A and ground. Okay, so that's our expression for IR in terms of voltage. And then for the capacitor current in terms of voltage, well, we just use the expression that's on the PowerPoint slide shown previously, where capacitor current is just C dV dt. So what you end up with, as you can see here, is a first order differential. And then on Polylearn, I have a handout that shows the solution of this first order differential equation. Okay, right here, where we find the natural response. Oh, also on this handout, there's a little description of the basics that we talked about on the PowerPoint. But as you can see, we first find the natural response, which is due to the stored energy of the capacitor, and then we come up with the forced response, which is due to the DC source in the circuit, and then the complete response, which is our answer that we're after. That's just the summation of the two responses, forced and natural. So we end up with this equation here that's a constant, the steady state voltage, times 1 minus a decaying exponential. So that's what you see in this bullet on the PowerPoint, that if you have an initially uncharged capacitor, for t greater than 0, the capacitor voltage is going to build up by this expression here of the final steady state voltage times 1 minus a decaying exponential, where this symbol here, this tau symbol, is the time constant of the circuit. So going back to my notepad here, here's what the capacitor voltage would look like for that circuit. That at t equals 0, there's 0 volts because initially there's no stored energy, but then that charge is going to build up across the plates of the capacitor as time progresses, so therefore the voltage will also build up, and given enough time, that voltage across the capacitor is going to charge up to the source voltage in this particular circuit. So right here, the RC, that's the tau, that's the time constant. Okay, resistance times capacitance has units of seconds time. So if you remember from your math, e to the minus 1, e to the minus 1 is approximately 0.36. E to the minus 2 is 0.135 approximately. I don't recall offhand what e to the minus 3 and e to the minus 4 are, but they're both smaller, of course, than both smaller than 0.135. But I do remember that e to the minus 5 is like 0.007. Okay, so if you were to plug these numbers here, you would see that after one time constant, if we put in t equal to RC, we'd get e to the minus 1. So then you have inside the parentheses 1 minus 0.36. So after one time constant, you're going to be, so you call this tau, 1 tau, your voltage is going to be 64% of the steady state value, the final value, Vs. Okay, because you get 1 minus 0.36, which is 0.64. And then after two time constants, you'd have e to the minus 2 here. So now, now you're going to be at about 85%. Okay, what would that be? Well, actually it'd be 86.5% of the final value. And then after 5 time constants, okay, where t equals 5 RC, this would be e to the minus 5. So you'd have 1 minus 0.007. So now, for all practical purposes, you're at the final value. You're 99.3% there. So this is important to realize, because in practice we'll say that a capacitor will reach its final voltage at 5 or more, or excuse me, at 5 time constants. That once we reach that 99.3% level, we just say that we're there. Where in theory, you might remember from your math that this type of curve is asymptotic, where in theory you don't reach the final value until t equal to infinity. Okay, but in practice we'll just say at 5 time constants, we're at the final value, we're at steady state. Now, as this is happening with the voltage, the current for the capacitor is actually decaying exponentially in time. Okay, and you can see this mathematically by the expression c dv dt, that if we take the derivative of this expression here, we end up with Vs over R e to the minus t over Rc, the time constant. So you can see this is a decaying exponential. So as the capacitor is gaining stored energy, and we say that the capacitor is charging when it's gaining stored energy over time, the current for the capacitor is diminishing. Okay, so you can see that mathematically, but also if we go back to our circuit, see, it should make sense that as the voltage across the capacitor is building up, that the current for the capacitor would be decreasing. Because if you just look at the circuit here, once this switch closes at t equals 0, well, for all time past t equals 0, you're going to have Vs as your voltage on the left side of this resistor, okay, this node here. Because once the switch closes, this is all the same node, the plus side of the Vs source and the left side of the resistor. So you got a constant voltage here. But in node A, which is equal to the voltage across the capacitor, well, that's the voltage that's building up over time. So you got a constant voltage on this side, you have that voltage that's building up over time on this side. So the voltage difference across this resistor as time progresses is going to get smaller and smaller, and therefore its current's going to get smaller and smaller. And since this resistor is in series with this capacitor, well, the capacitor current will get smaller and smaller and smaller as time goes on. Okay, so that explains this bullet here on our slide. Now, the next bullet, this is when we discharge a capacitor. Okay, this is when we take an initially charged capacitor and at t equals 0 connect it up to a resistance. So if we go back to our notebook here and look right here, here would be the circuit for a discharge case where the capacitor is giving up its stored energy over time. So here there's an initial voltage across the capacitor that we have labeled V0, and then when the switch closes, that provides a path for the current to flow from this capacitor to where the resistor is. See, once that switch closes, the current's going to flow like that from the higher end of the capacitor, higher end voltage of the capacitor to the lower end. So here, since we don't have a source, we only have the capacitor, well, we only have stored energy, so only a natural response, which if you look back at the derivation earlier, the natural response was the decaying exponential. So when a capacitor discharges, both its voltage and its current decrease exponentially. Okay, so see, that's why both cases the current has the same form. It's the same decaying current as we saw. So those are, or that covers, basics of capacitors. we're going to do more. We're going to get to a technique of solving circuits with capacitors along with resistors, first order circuits, where we use a circuits approach to solve for voltage and current as opposed to a mathematical approach with differential equations. But let's move on to inductors. Here's some basics of inductors. Inductors have units of henries. An inductor is, or inductance, is the ability to store electrical energy in the form of a magnetic field. And your basic fabrication of an inductor is that you take wire and wind it up. Sometimes you just have what's called an iron core. You'll just wind the wire into a loop. Other times you'll take the wire and you'll wrap it around some iron, okay, which actually improves your inductance. Okay, inductance depends on things like the number of turns you have, the diameter of the wire, and then also the material that you wind the wire on. Okay, everything else being equal, an inductor that's wound on an iron core is going to have more inductance, okay, more ability to store electrical energy in the form of a magnetic field than a wire that's wound just in a loop, okay, around air. Well, from physics, here's a relationship between magnetic flux and current, and you can see that it's a direct relationship. L is what we use as our symbol for inductance. And then here's an expression for Faraday's law, okay, that voltage is equal to the time rate of change of magnetic flux. So to get our circuit equation for an inductor that relates the voltage across an inductor to its current, we just take this expression here for magnetic flux and plug it into Faraday's law, and that's where this VL equal to L di dt comes from. So for an inductor, it's the current that cannot change abruptly. Okay, remember, for the capacitor, it's voltage that cannot change abruptly. Okay, inductors, it's the current. Again, you can see it mathematically here with the dt. Another way to reason it is that when current changes through an inductor, that's going to create a voltage across the inductor that will oppose the current flowing through it. So as current increases through an inductor and the magnetic field expands, the induced voltage across the inductor is going to be a polarity such that it opposes that current that created it. Okay, so that's why, or that's a way to reason that it takes time for the current to increase through an inductor because of that, what's called back EMF. Now, I have a handout just like the one for the capacitor on inductors. Okay, at the top of the handout goes through some of the basics that are on the slide, and then if you were to have an inductor in the same type of circuit that we had the capacitor for, and you did the circuit theory and went through to solve for its current, you would see that you get the same form of expression as we did for the capacitor. The only difference is that we have current now instead of voltage. Okay, so it's going to be a curve just like what we had for the capacitor case, okay, right here, except Vc of t now would be IL of t. Okay, so it's the same 1 minus decaying exponential type of curve, but current instead of voltage. And for an inductor, it's going to be the voltage that decays exponentially over time instead of the current. Okay, and then if you have an initially energized inductor, meaning that you have an inductor that has stored energy at t equals 0, and then you connect it to a resistance, well, its current is going to decay exponentially along with its voltage, just like in the capacitor case. Alright, so yeah, the purpose of this lecture was just to go over some of the basics of these storage elements. Again, I would imagine most of the things we talked about here were covered in your physics class. Actually, one added important item here is that the time constant for an inductor is different than the capacitor case. Because remember, for an RC, okay, for an RC, that's tau. Okay, R times C is your time constant. For an RL circuit, your tau is equal to inductance divided by resistance. Okay, so that's your time constant. I think it's a good practice to, on your own, take the units of resistance, which are ohms, which is equal to voltage over current, or volt per amp, and then multiply times farads, which is equal to coulombs per volt, and prove to yourself that you get units of time, which are seconds. And then do the same thing for the time constant of an RL circuit. Okay, take units L and units R and prove to yourself that you get units of time. And then you'll never forget that, well, one, you won't get the equations wrong, and also you'll never forget that you know, these expressions are called time constants for a good reason, because they actually do have units of time. Okay, so in the next few lectures, what we're going to be doing is learning a technique to solve circuits that have these storage elements where you don't have to solve the circuit using a differential equation. You can use circuit techniques to come up with those exponential curves, whether it be voltage or current, and whether it be an inductor or a capacitor.